Hello, and welcome to Biology. I'm your host, Tom Willis. We'll be going through the journey of life together. Now, let's open our books to 13.2. That's pretty good, isn't it?
Next time, you should be looking at your book and then just be like...
Somebody told me to make like a little song that you can put at the entrance of each one. We need to think about that. We need to work on that.
Like building out a science guy, but we're gonna make it tiny.
Exactly. Okay.
That's copyright infringement.
Page 401.
Claire's dad is Bill Nye.
Alright, I know it's late in the week. We're almost done with school, but we need to talk about the origins of life. Very interesting stuff here.
Watch out for books out.
What page?
You guys are quick out.
401.
Alright, look it up, guy.
Ew, what was that? Go back.
Hey, what was that? Go back.
You creature.
That's a
It
person.
looks like a person with garlic and
There's a picture of
Go back again.
Ew.
That thing.
Okay.
Oh, that's sad.
Elephant.
The frozen baby mammoth.
Why did they froze that?
They found it frozen in the ice. They're extinct, you know? They're thinking maybe they can take a cell from that and clone it
Ew.
and have an elephant give birth to a mammoth.
That'd be so cool.
And then we can bring back the mammoths,
Awesome.
even though they're extinct.
What about the Serengeti tigers?
wrong.
If we found one frozen, maybe those too.
What's the one that I think?
Yes,
We should write them a letter and tell them.
No, let's not bring that.
they're working on it.
No.
Wait,
You don't have to write 'em.
saber-tooth
Bring
tigers.
dinosaurs back.
With the saber-tooth tigers from Mercury too.
T-Rex.
Yep.
Let's make a dog.
Okay,
Oh, obviously we're going.
my turn. My turn. All right. Scientists have long been asking the question, where does life come from? And of course there's the religious explanations, but is there any other explanations? And since we're in a science class, that's what we deal with in here. So let's see if there's any scientific research into the question. And a guy named Francisco Redi, that's this guy, did one of the first experiments to test the theory of spontaneous generation. Spontaneous generation is a theory that says that life can come from non-living stuff. And one of the old bits of evidence for spontaneous generation was this: if you set out an old piece of meat that's dead, and you wait a few days, maggots will appear on the meat. And back in the 1700s and 1600s, they said that's an example of spontaneous generation.
Wait,
The
where did they come
maggots
from?
were somehow born from the dead meat. Well, Francisco Redi, a scientist in the 1600s, did an experiment to disprove spontaneous generation. And here was his experiment. If he put meat in a flask and left the top open, maggots did appear a few days later. But if he put meat in a flask and had the top stoppered, maggots never appeared. Because he realized that maggots actually are baby flies, and they came from flies laying their eggs. And the eggs are microscopic and you can't see them.
So, like, if we were, I don't know, eating lunch and a fly landed on it, basically we have a bunch of maggots in our body?
No, because the eggs take a long time before they hatch. They take several
Oh.
days. So if you left the meat out for several days, but once you swallow it, it gets in your stomach and the digestive juices to break it down.
So we have a bunch of, until it breaks it down, we have a bunch of maggot eggs.
Dead baby.
There could be fly eggs, yeah. If a fly lays long enough to lay eggs. That doesn't hurt you. You'll digest those too.
Oh my god.
Now, here is another experiment done by a famous scientist named Louis Pasteur. You've probably heard of him. He invented a process called pasteurization that keeps your milk from spoiling too fast. Used to be milk only lasted one day, and every day the milkman came and he dropped off new milk at your doorstep. But nowadays milk lasts 2 to 3 weeks because of this process called pasteurization.
I'm mad about
Yes.
this.
So when did Pasteur make this?
He was back in the 1700s.
Is that what they call cow pasteurization?
No, Pasteur different. He was a French scientist. Now, here was the thing. He knew that if you left broth, if you took broth is like soup, and you boiled it and left the soup out, it would spoil. And spoiling is growth of bacterium in the broth. That's what spoiling is. Y'all need to pay attention here. It's not easy.
I probably can.
He has a switch. In the sense of
However, if you take a swan neck flask, this is called a swan neck flask, and you boil the broth, as long as the swan neck flask is kept upright, it'll never spoil. However, if you turn the swan neck flask over, the broth runs down the neck and touches this area. So you tip it over so the broth touches that area, and then you tip it back so that it goes back in. It'll spoil. And what Pasteur figured out are there are little tiny microbes floating around in the air that settle down through the opening in the swan neck and will settle right there. And if you move some broth up to touch that area and it goes back, the bacteria will now be inside the flask and it will cause it to spoil. Pasteur basically proved that there are bacteria even floating around in the air. And it's true that we breathe about 3 of them in with every breath. It doesn't hurt us. We have cells that can deal with them and kill them. So, spontaneous generation through these 2 famous experiments has been shown not to be real. That's not how life comes about. Life doesn't come from lifelessness. You want to see a stupid video about spontaneous generation?
I want to see a
Yes.
stupid video about spontaneous.
I knew you did.
No, I don't.
Here we
The
go.
last stupid video I watched is very stupid.
This is stupid too.
This is wonderful. Candlelit dinner at a French restaurant. Bread is hot. Wine has bouquet. Get down the soup. Garçon! Garçon!
Oui, oui, monsieur.
There's a fly in my soup.
But of course, monsieur.
This is an outrage.
No, monsieur. This is spontaneous generation.
What?
You know spontaneous generation, the process by which life, our little friend, is produced from non-living matter.
Oh, that's garbage.
No, that's bouillabaisse.
Everyone knows that Louis Pasteur disproved the theory of spontaneous generation over 100 years ago.
Well, if that is the case, then what is that fly doing in your soup?
See? It was stupid. So, if it's not spontaneous generation, how could living things arise? Well, here's another theory. It was proposed by a guy named Alexander Oparin. Oparin was a Russian scientist who studied rocks. And he studied what the Earth's early atmosphere was like.
Can we open the blind?
Huh?
Open the blinds?
Too dark?
Yeah.
Okay. Good job, Nancy. Better?
Mm-hmm.
Now, Oparin studied the gases in Earth's early atmosphere. And he noticed that the gases in Earth's early atmosphere, let's go back a little bit here to our last lecture. I don't know if you remember this picture right here. He noticed that the gases in Earth's early atmosphere contain the same atoms that living things are made of. I don't know if you remember chapter 1, but all living things are made of basically 6 atoms. Carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, chunks.
Bromine.
99% of your body and the body of that tree out there and the body of every living thing are made of chunks. And Oparin noticed that the molecules of the atmosphere had carbon, hydrogen, oxygen, nitrogen, sulfur. And he knew that phosphorus makes up rocks. So all these atoms were present in early Earth. And operants supposed, he wondered, hey, is there any possibility that these molecules could somehow have bumped into one another to make the first living cells? That was operant's hypothesis. Anthony, are you with me here?
I'm with you, bro.
Pick your head up. Take your hood off. Make sure I know that you're paying attention. That'd be good. So, that was operant's hypothesis. Maybe somehow the gases in early Earth's atmosphere bumped into one another, and that could make a living thing. Well, 20, 30 years went by, and then a couple scientists came along who wanted to test this theory. Those scientists were named Miller and Urey. Miller and Urey were famous scientists who tested that hypothesis. How did they do it? Well, this is their experiment. And it's in your book on page 403. What they did was they took this setup and they put the gases from Earth's early atmosphere into this chamber here. And they shot electric sparks through it. They put methane, ammonia, hydrogen gases into this tank, put electricity through it, and condensed it, meaning cooled it off, and they took a look down here at what they got. And just by those molecules bashing together for about 2 weeks, you know what they found? They found organic molecules. They found the molecules of life that we studied. There's Miller looking at his experiment.
How recently was that?
What did they find? They found fatty acids, glucose, amino acids, nucleotides, the molecules that make up DNA. These are the 4 types of organic molecules that we studied. Sugars, fats, proteins, and nucleic acids. Purines and pyrimidines, remember, are types of nucleotide. So those will naturally form just from gases banging together. You see, molecules, when they hit each other, they stick to one another, and they make bigger molecules. And that was done, Hogan, you're asking when that was done. This original experiment was done in the 50s, but they have continued doing experiments like it. These guys won the Nobel Prize for it in the 1950s. This is a clue that maybe the molecules that make up cells could form naturally. Video footage of their experiment.
In this experiment, Miller and Urey mixed water vapor, or steam, with ammonia, methane, and hydrogen gases. An electric current simulating lightning was passed through the mixture. The mixture of gases was cooled, producing a liquid that simulated rain. Miller and Urey collected the liquid in a flask. After a week, they analyzed the chemicals in the flask and found several kinds of amino acids, sugars, and other small organic molecules.
So, we get this picture of early Earth with these organic molecules falling out of this atmosphere because they're heavier. After the atmospheric molecules stick together, they form these heavy things that fall out and fall into the oceans. And we say that the oceans back then were an organic soup. You may have heard that before. Also called a primordial soup. And what that means is the oceans were like soup. If you go back in time 3 billion years ago, with a spoon, you could eat the ocean. They had sugars in it, and fats, and proteins in it, and nucleic acids. You could literally eat the ocean. It would have tasted good. Wouldn't be nasty and just salt like it is now. It would have nutrients in it. So the oceans were an organic soup back then. The experiment proves that must have happened. If they formed it just from 2 weeks of knocking into one another, think how much of this stuff you get through 100 million years of collisions in the atmosphere. Yes, okay.
So, I'm sure like this caused it, but why are our oceans now just like basically pure salt? I mean, it's water.
Because all of these nutrients have been removed.
Okay.
Because the organisms, the first organisms that evolved, you know what they ate?
The stuff in it.
They ate the soup
And
that was
left the
around them,
salt.
and eventually, yeah, they left the salts, and eventually all that was gone. We're going to get to that. So what we think is that the first organisms somehow, whoops, let me go back. Huh, I don't have it on this. Hold on, I gotta go to the big AP bio. I haven't got this one perfect yet. I left out some stuff. Where is it? Here it is. Sorry. This is the AP Biology. Okay.
Back off, man. I'm a scientist.
What movie?
Back off, man. I'm a scientist.
Back off, man. I'm a scientist.
Back off, man. I'm a scientist.
Alien vs. Predator.
Nope.
Jurassic Park.
Ghostbusters.
Called it.
It's the guy with glasses who says that, isn't it?
Dan Aykroyd.
No, it's that was Bill Murray.
Steve Martin.
Okay. So scientists have continued these experiments. Listen. Scientists have continued these experiments. They've continued to let these molecules bash together in chambers. And they've been doing this for the last 50 years, ever since the Miller-Urey experiment. And they wanted to see if they could make an organism, a living thing, out of just letting the molecules hit together. And after you do it for many months and years, the molecules make larger structures. These are called proteinoids. They're big balls of protein that looks a little like round cells. And these are called lysosomes. They're spheres of lipids, of fats, like phospholipids. Like, remember the phospholipid bilayer? And these liposomes behave really cool. They grow larger and larger by absorbing fats from the ocean. And guess what happens when they get big? They split in two. Kind of like a cell reproducing. And by continuing to let the liposomes and these proteinoids bash together for years and years, protocells have been made in the labs. Protocells are objects that look a lot like cells, that absorb nutrients from their environment and grow larger and larger and split into two. They're not quite cells, living cells, because they don't contain DNA. And you would need DNA to be a living cell like our cells are. But they've gotten very close, scientists have. So they call these things protocells. So scientists describe the formation of the first living cell in this way. That there was a time of chemical evolution when molecules bashed together to make larger molecules. And then finally, these protocells, they've done all of this in the lab, all the way from inorganic chemicals, all the way to macromolecules and membranes, all the way to protocells. If protocells could absorb nucleotides and make a DNA strand, they would have a living cell made in the lab. Scientists think they're going to be able to do this within the next 15 years or so. Now, does that mean that's how the first cells were made?
No.
Not for sure, but it's evidence toward that. It's evidence toward the fact that that could possibly happen. There's no way we'll ever know because we can't go back in time. But we do know through detective work a lot about early Earth. And if those molecules were present in early Earth's atmosphere, they should have combined in these ways. Yes?
Do you think it's possible for them to make a time machine?
I don't. Not now, but maybe
Like
way in
in
the
the future?
future.
They'll
Maybe.
figure out a way like
We could actually go into the future, but not into the past.
Why can't we go? Well,
Because as you travel closer to the speed of light, time slows down for you, and so you can kind of skip into the future. Take astronomy if you're interested in that kind of thing. We talk all about it. But I can't really talk about it here.
Okay.
I want to show you a video of what it was like on early Earth. This is a cool video. It's kind of scary.
I should do it right now.
Planet Earth at the beginning, 4.6 billion years ago. Its surface erupted in a sea of molten magma. A billion years later, the planet was in the midst of a slow cooling process. Vapor rose to the sky, condensed, and fell to Earth in a torrential downpour. In the aftermath of the seemingly endless deluge, the primordial ocean was born. The atmosphere after the formation of the ocean was heavy with carbon dioxide, much like the planet Venus today. Earth was sealed off by thick clouds, and the lone streaks of sunlight that penetrated the cloud mass tinted the sky orange. Earth was like a giant steam bath with ocean temperatures soaring over 300 degrees Fahrenheit. But in this primordial soup, the building blocks of life were accumulating. Meteorites showered the Earth, perhaps bringing amino acids necessary for the formation of life. And then one day, 4.5 billion years ago, an asteroid the size of Mars collided head-on with Earth. This giant impact was the greatest event in our planet's early history. The impact was of such phenomenal magnitude that it carved out part of the Earth's mantle and hurled it into outer space. A portion of the torn mantle was drawn back to Earth. The fragments of debris scattered into space were swept up by powerful gravitational forces. They formed a new satellite, which would eventually circle the Earth. This was the birth of the moon. The giant impact shook the Earth to its core. On the ocean floor, rows of hydrothermal chimneys surfaced, spouting molten rock and volatile chemicals. Sentinel, the moon stood watch over the roiling seas. The distance between Earth and the moon was half what it is today, creating huge ocean swells and enormous tides with its gravitational pull. As the primordial ocean simmered, chemical reactions created complex new molecules. Some, such as hydrogen cyanide, would have been lethal to humans. Tiny molecules of these toxic compounds combined to form larger ones. Out of this mix, other molecules that would eventually form DNA, the blueprint of a living cell, took shape. This first step toward life would take nearly 1 billion years to complete. Eons later, no one can explain how the graceful double helix formed, transforming inanimate compounds into living cells, cells that can grow and reproduce. The catalyst of life remains unknown.
Pretty cool on the earlier
I
end,
need
huh?
new shorts.
People who criticize this theory will often argue like this. They'll say, come on, that's like making a cell that's very complex and beautiful in the way it works out of a bunch of molecules that have just collided is like throwing a bunch of metal up into the air and a watch falling out. It's impossible. But what those people don't understand is, if you throw metal up in the air and metal hits each other, it doesn't stick together. But molecules behave a lot differently than that. When molecules collide, if the conditions are right, if it's warm enough, and if there's a liquid medium that the molecules move around in, they'll hit each other and they'll stick to one another. And that happens without having to do anything. It's just as long as the molecules are moving, they're going to hit one another, and they often stick. Now, a lot of times they stick in the wrong arrangements, and it doesn't make anything that'll stay together for very long. It just falls back apart. But if it sticks in the right way, it'll make something that's very, very stable. For instance, the glucose molecule. A glucose molecule, that C6H12O6, remember that we studied? That's a very stable molecule. It'll stay together in that shape for millions or even billions of years. Very stable. And so sometimes you get things bashing together and they find the stable arrangement and they'll stay that way and they'll be nice and stable and big. And if they bash into other things, they might make another arrangement that's nice and stable and big. And these molecules, you let them bash together long enough, they make these stable arrangements. So that's a way that possibly complex cells could have formed. Would have taken probably a long time, but from the time the Earth formed till the time we see the first life forms was about 600 million years. Now scientists have made protocells in the lab in only 50 years. Imagine a whole ocean of these molecules bashing together for 600 million years. Perhaps you could get stuff that's even more complex than what we've made. So just something to think about, a possibility of the way life could have formed. And it will be very interesting to see. And this is something you can look for in your life if it ever happens. Take notice of it. It'll be a big announcement one day if they ever make life in the lab through just collisions. If that ever happens, that would be the first life form that came about that had no parents in the last 4.5 billion years since the first cells came around. Wouldn't that be cool? You might hear about that happening sometime in your lifetime. New life in the lab. So, interesting stuff.
Are we done?
No, we're not quite done. I want to go back to the other thing. I want to show you one other thing, and then we'll be done. Uno mas. Oh.
If
Yes.
If I have a question about one of your sound clips, do I need to save it for after class?
If you do what?
If I have a question about one of your sound clips, do you want me to save it for after class?
What is it?
It's what part in Ghostbusters was that clip from?
Back off, man. I'm a scientist.
Yes, sir.
The guy from the EPA comes in and demands to see their storage facility.
Oh.
Gets up in his face and he goes back off.
Right before they let them all out.
Yeah, I think so.
I got you.
Okay, one other thing I want to show you. Okay, help protect me from unknown content.
I just didn't go out.
I'm not like a portrait, dude.
What a pet man.
I'm not Candace.
Yeah, I'll draw
That is good.
Okay, in your book on the top of page 407, shows how we think complicated cells form. Top of 407. What we think happened is that an early cell took in other cells. Y'all remember mitochondrions, don't you? What were they?
The powerhouse of the cell.
The powerhouse of the cell. We think mitochondrions used to exist on their own by themselves. Not inside cells, that they were cells on their own. Why do we think that? Because if you look inside a mitochondrion, it's got its own DNA inside of it. It's called mitochondrial DNA. And if you watch mitochondrions moving around inside cells, they'll divide on their own, just like a bacteria will. So we think what mitochondrions were, they used to be free living, and they were sucked inside of other cells. And so that the new cells get mitochondrions through what we call, when cells work together, I can't remember the name. Anyone help me? Two things, living, working together, helping each other.
Coexist.
Teamwork.
Coexist.
Coexist.
Through mutualism. You ever heard of mutualism?
Hey.
Organisms living together and working together. So that these things, which could make a lot of ATP, listen, these things could make a lot of ATP, they lived inside these cells that were good at protecting them. And then you have this new cell that now has mitochondrions in it. That's the animal cells we have today. Some of those early cells took in cyanobacteria, which are photosynthesizing bacteria that can make their own food, and took those in, and those became the chloroplasts. So chloroplasts and mitochondrions, we think, were originally free living cells that were taken into other cells. And now we have these cells that have a bunch of different organelles in them. They're kind of a mixture of cells that used to live on their own. More complicated cell. Do you know what we call a cell that's more complicated and has all these different types of organelles and structures? Starts with an E. Eukaryotic. Very good. J's all over it. Okay? So we think eukaryotic cells came from prokaryotic cells that now live together. And so that's a little insight towards life. So what you do tonight is you read 14.2. You can read it Saturday night or Sunday night or tonight.
Sunday morning.
14.2, it's a few pages, and then we'll do 14.3 next time. Thank you for joining me in our journey. Willis out.
Oh.